Welcome to all. Today's the lecture for the application of Laplace equation. Yesterday I have discussed with you people the derivation. Now I am going to discuss its numerical or the application of Laplace equation. So we are having the question, you can see on the screen, solve this Laplace equation subject to these boundary conditions. The conditions are u0y and uly is 0, uxm is 0 and ux0 is f of x, where y varies from 0 to m and x varies from 0 to l. So let us solve this numerical now. First of all, we are having the Laplace equation given as this, and the three possible solutions from the derivation that we have discussed it in the yesterday's lecture. They are given by 2, 3 and 4. So now I will use all the given conditions one by one for these three solutions, and I'll continue with that solution which is feasible with these boundary conditions. So the very much first condition is u0y is 0 and uly is 0, means to say when x is 0 and x is L, y is fixed, the value of u is 0. So let us put this conditions in equation number 2. I got C2 is 0. So if I put if I impose the second condition uly equal to 0 in second, I got C1 is 0. So if C1, C2 are 0, we are having u as 0 from second equation, which is a 0 solution, which is not feasible. I want the non-zero solution. So let us apply these conditions from in the third solution. If I put these values in third condition, I got one equation like c5 plus c6 is 0. You can put and can check. And if I put x is equal to L and taking y as fixed, I got this one. For non-zero solution, I will take this as 0. So c5 plus c6 is 0 and c5 e to the power pl plus c6 e to the power minus pl is 0. So this is a homogeneous system of equation. Okay, for non-zero solution c5 and c6 should be 0. So again we are having the 0 solution, for that's why I am going to reject this solution also. So let us imply these boundary conditions one by one in solution number 4, which corresponds to k is equal to minus p square, that is when k is negative. So u0y is 0, we got c9 into c11 e to the power py plus c12 e to the power minus py is 0. So again for the non-zero solution, we will take c9 as 0. Let us apply the second condition in fourth, that is uly is equal to 0. So put x is equal to L, and using c9 equal to 0, we are having this one. Again for the non-zero solution, we will have sin pl is 0. So if sin pl is 0, we will be having pl is equals to n pi, where n is an integer. So p is equals to n pi over n. Now I am going to use a third condition in the fourth solution, because fourth solution is feasible solution. uxm is 0. Now I am keeping x as fixed over here and taking the value of y as m. So if I put all the values in the fourth solution, I got this one. You can see on the screen also. I am using c9 equal to 0 and p is equal to n pi over L in this solution. I got this one. You can see on the screen also. Again for non-zero solution, we are having c11 e to the power n pi m over L plus c12 e to the power minus m pi over L is 0. So you can say one factorial take on the right hand side. So c11 is minus c12 e to the power minus n pi over L over e to the power n pi L over m. So the denominator is base is same, so powers will be the factors are being divided, so powers will be get subtracted. So from fourth solution, if I put all these values in fourth, I will get this one. Multiply or simplifying, taking the common factor as the factor e to the power minus 2n pi m over L can be broken into like e to the power minus n pi m over L over e to the power n pi m over L. So after simplifying, you can see on the screen, after calculation you will get u as this one, and this c10 c12 can be replaced with the constant an with also the factor 2, including the factor 2. So the general solution will be given by putting the sign sigma. So u is sigma n varies from 1 to infinity an sin n pi over L m minus y sin n pi x over L e to the power minus n pi m over L. So I am using here the shine. Shine means the hyperbolic function. So shine x, I have sometimes discussed in the class that shine x is e to the power x minus e to the power minus x by 2. So here the factor x is being replaced with n pi m minus y over L. So this factor reduces to shine n pi m minus y over L. So again, this factor e to the power minus n pi m over l into an is replaced with the constant en. So you can see the solution given by equation number 5. So the last condition is ux0 is f of x in fifth. So if I put y is equal to 0, I will get this one condition. So this is your half range Fourier sine series where en into sine n pi m over l can be given by 2 by l integral 0 to l f of x sine n pi x over l dx, as I have discussed it so many times in my class. So from here en can be evaluated, that sine factor will go into the denominator on the right hand side, that will become cosecant, that is the reciprocal of sine x. So therefore the solution of the given equation, Laplace equation, is given by equation number 5, and in 5 we are having the another factor en which is being calculated by equation number 6. So this is the main application or the numerical of the Laplace equation. So you can go through the whole numerical with pen and paper on yourself, and if you find any kind of difficulty, you can make me a call, you can WhatsApp me, or you can Gmail me. Hope so the lecture is much more clear to you.